Okay, so let me start by thanking the organizers for this wonderful meeting. I had to arrive late, but already had some great discussions. So I'm going to discuss a recent paper and a lot of ongoing work that it's generating with these wonderful collaborators, Raphael Flounder, Meredith Merkelai, and Leonardo Senatore, along with others involved in the next steps. So this is a brief outline. We heard a beautiful review of the whole subject by Daniel earlier, so I'll be able to hopefully explain this clearly without background. In this talk in particular, I'm going to be discussing the sensitivity that non-Gaussian correlators have at all n to heavy field production. And this is partly motivated by the physics and couplings that axions have in string theory. That is a more general interest. I'll explain that. I'll explain the shapes and the amplitudes of these endpoint functions, which have some interesting features, one of which is that they are, this is very easy to have happen, they are orthogonal to previously analyzed shapes of non-Gaussianity. And somewhat more interesting or novel is that they can have a growth of signal noise with the number of points n, which will lead us to consider the whole probability distribution, which will play more of a role than it usually does. So I'll discuss that and what we're aiming for with the analysis toward the end. Okay, so as we did just hear in the first talk, cosmological data is wonderfully precise, and it gives us truly interesting constraints on what was going on 14 billion years ago in terms of the contents and interactions of the theory. And some possibilities for this have been constrained as much as possible in the CMB, but most haven't, because it's an infinite dimensional space. It's a reasonable subject to talk about at strings, because string theory has kind of had an unreasonable impact on the subject. It's generated interesting dynamical mechanisms which have opened our eyes to the range of inflationary dynamics and signatures, which then get incorporated in the effective field theory treatment that Daniel reviewed so beautifully, and even data analysis. So today's talk will, in a nutshell, be a new example in this tradition with some novel features and have some new tests. So let me, again, referring to Daniel's talk, he did a beautiful job from the bottom up. Let me very briefly review how things went from the top down. So in single field slow roll inflation, non-Gaussianity can be studied and wanted the proper calculation in 2002. But it's small because the dimension is flat and the kinetic term is simple. It was already known, of course, that if you don't have just a single field but have additional fields, those transverse directions are not so constrained. They can be quite nonlinear. But even for a single field, and this was the first thing that string theory injected into the subject, it happens that self-interactions can, for very simple reasons really, slow the field down and produce inflation, which just requires a slowly varying pixel, in a way that's very different from single field slow roll inflation. And not surprisingly, with those self-interactions slowing the field as part of the background solution, the perturbations are that much more non-Gaussian. Okay. And there's other contributions to non-Gaussianity, including the two I've listed here. The second one is one that we heard a lot about this morning. The first one is something I also need to compare to what we're doing today, which is resonant non-Gaussianity, and is what you get from a simple model motivated again by axion physics with a sinusoidal correction to the potential. So in that context, the thing I want to focus on is the way that the signal to noise ratio of the non-Gaussianity in that type of dynamics is, in any weakly coupled version, which we have control over, less than 1 is bounded by 1. Well, as I mentioned already, that will contrast with what we find in the dynamics we talk about today, which also can be compared and contrasted to this quasi-single field idea where you consider massive particles produced just by virtue of the Hubble expansion, magnitude higher scale in energies. So in a nutshell, the dynamics I'm referring to is following: couple the inflaton to some heavy fields, and again, as Henry said, in string theory, things couple to other things quite generically. And this can happen in a way that doesn't ruin the overall trend of inflation, either through a regular periodic effect, say, through symmetry arguments, or in a more random way. Once you have that dependence of some massive field, mass m chi, on the background evolution inflaton, that's a time-dependent action for it, and it's produced at some level, with a characteristic scale being the scale of the time dependence in this context of a background solution that's basically slow roll inflation. That's the SPY scale, the 58 squared times Hubble squared. So when these particles are produced, this coupling to background solution also entails a coupling to the perturbations of the scalar field phi, and hence automatically to some radiation of these delta phi perturbations, which we'll calculate. And the amplitude is this exponential written here. In terms of the sensitivity of observations to it, the basic estimate you would do is to expect a sensitivity that's given by 1 over the square root of n, where n is the number of pixels in the map. And we'll see that a very detailed analysis bears that out, leading to a novel shape of the input functions and different ranges of parameters, but in some of them, as I keep emphasizing, the signal to noise control of n, which is an interesting new thing. So in terms of the scales, we already heard about this. We're jacking it up to this 58 relative to the Hubble scale, and then bigger factor 5 or 6 above that. And again, the picture is the inflaton can couple to other degrees of freedom. In string theory, we have many candidates in this KK modes that feel the motion of the background inflaton field and other things, moduli noise, etc. And again, they can do this in a regular way, which is the case we'll study in detail, but they can also do it in a more random way, and more general way. And we'll eventually get to methods for constraining all of the above. So if you think about this from the bottom up, the point is just that effective field theory of inflationary perturbations has in it arbitrary functions of time, even in the truly single field level. And because the data can be sensitive to even these exponentially suppressed effects, we can't safely integrate out fields that are even heavier than this Phi-dot scale. And hence, the single field version of the model is less relevant than you might even think, given the scales. So you might wonder how it is that this exponential effect can be important, given that these fields do also generate, through radial corrections or just integrating them out classically, contributions that are power law suppressed in their mass. And the reason for that is just that the details matter. In essence, our results have this exponential times a large prefactor. So the non-Gaussianity from these power law effects of the massive field mass m are on the top line here. They are the power law effects, and if you just trace that through and estimate the non-Gaussianity in a reasonable, crude way, taking the ratio of the 3 to 2 point part of the Lagrangian, you find that it's a tiny effect. But it does lose to this effect that is proportional to this exponentially small thing I keep emphasizing because of power law prefactors that I'll briefly explain that depend on this ratio of 6 orders of magnitude. Okay, so this is a somewhat general thing, but two cases are rather directly motivated by axion monogamy. The structure there with the branches and the potential is mirrored in a branch structure of the excitations of the theory as well. So higher four-dimension objects in the theory also have the same kind of branch structure. And that means that each of the underlying periods, some new sector comes down, becomes as light as it's become, and then gets heavier again. That'll be the case that we call case A. Another case is simply that the underlying periodicity of axions in string theory means that the other fields that are around feel that periodicity, and their masses, like moduli, the string application, and so on, can't help but get some level of modulation as a result. And so, just because of that, we expect contributions to the mass squared segment or sinusoidal, so we'll analyze that case, which we call case B. And in fact, the first thing generates a second Weinberg calculation as well. So again, this could be studied more generally, including in the opposite regime, where it's a random distribution of mass dependencies. So radial corrections are always important. Here we're not concerned with a very particular model, but we did want to make sure that there wasn't any radiative correction that is intrinsic to the supersymmetry breaking of the time-dependent background, which would constrain the level of these couplings and hence the level of the non-Gaussianity. So obviously the larger the couplings are, the larger the nonlinear effects could be. So it's an important point. But in fact, there's no really useful constraint from that. If you imagine some level of microscopic supersymmetry, qualitatively, of course, in loops, bosons and fermions cancel, and non-adiabatic effects, they don't. They add up. So that's roughly speaking why there's no reason for a direct parametric cancellation of this. We also pose the usual slew of consistency conditions scenario. Partly for simplicity here, we insist that it's the underlying inflationary model is slow roll. So these high fields, these heavy fields that are produced don't back react on the evolution in a significant way. Of course, there are interesting scenarios where that isn't true, but let's just be clear about this one. Okay, so in slightly more detail, how am I doing on time? The time-dependent mass means source for these delta phi's, as I explained. The background homogeneous motion is a time-dependent homogeneous action for these heavy fields, which excites them. In the leading approximation, that generates a squeeze state in which then the delta phi fields are produced. So there are many contributions. I'll give the general formula shortly. But the one that leads in an interesting regime of parameters is a very physical one, which is basically a three-point function of two of these pi fields and a delta phi. So you produce a source from that interaction whose correlation functions. So you produce a source of delta phi's, which have correlation functions that are essentially +1. They have endpoint functions which are all proportional to the density of produced pi particles here. And the formula for that is the one which shows the power law enhancement that I mentioned earlier. So there's the slide out to the 3 house, the exponential, and then the double expansion. Okay, so you produce the source, and to compute the correlators of the delta phi perturbations just involves, let me get there, integrating that source against the de Sitter-Green's function for those perturbations. But before getting there, let me, for the record, write down a fully general calculation, which is the in correlator of these delta phi's in the full model, including the chi fields, which cannot be integrated out. And the time-dependent evolution will generate the appropriate squeeze state, which we can change variables and just introduce into the in calculation. There's a lot of diagrams that can contribute. The ones that I was just describing in words are these ones with 3-point vertices. So the blue lines here describe a pair of produced chi particles with delta phi lines coming off. And those can come off in higher point vertices as well, which we'll talk about more when we get to the large n behavior. Okay. The ones I circled here can be leading in these low point functions, and they factorize in a way that's also useful for practical purposes. So the methods for computing this particle correction are very, very standard, so let me not dwell on it. But let me just say, for these two mass functions that I mentioned, we have the luxury of isolating the non-adiabatic timescale to isolated points, so we can just add up. So in the sinusoidal model, it's the minimum of the mass at each period, and the other one is the obvious minimum of these masses. But again, you can calculate it in full generality, and then integrate against the Green's functions to get the delta phi perturbation. So in terms of basic integral of the Green's function against the time-dependent mass, which can have saddle points, resonant saddle points that enhance the effect, these are the answers for the endpoint functions. They're all proportional to 1 power of the density of the produced fields. That's the underlying Poisson statistics of the source. And then these particular diagrams I circled are given by a single sum of a factor of identical product of identical factors as written here. And you can just calculate this in terms of the parameters that enter into the scenario. This integral of the Green's function against the time-varying mass, let me focus on this case B with the oscillating mass, has resonances, and it's those resonances that end up enhancing the amplitude of the non-Gaussian correlators by a factor of the square root of the frequency of events in units of time. So at the level of the signal and noise in the 3-point function to the power spectrum, and in fact, any such ratio of n plus 1 to n, there's a simple ratio given by some combination of coupling that I call CD times this over h. And for aficionados, again, this is, although some of the underlying motivation is similar to that resonance case I described earlier, this is quite different in that there it was understood that the signal to noise in the non-Gaussian is at most generically smaller than that in the power spectrum, but here it can go the other way. Okay, so that introduces some interesting further directions. But before I get there, even if we work in a regime where that ratio is smaller than 1, you can ask about the shape of the correlator, the shape of the 3-point function. Again, as Daniel briefly mentioned, there are some limited dimensional space of such things, and in this context, this shape that we calculate turns out to be have very low overlap with all the previous ones, including the resonant shape, and of course the scale invariant shapes discussed earlier. So it's being searched for separately as it needs to be, if we want to know the answer. But then again, this regime where it grows with n is even more interesting, at least more novel, and in that case, of course, the 3-point function is not looking to go up an n or talk about the whole distribution. Okay, so because this is also turned out to be interesting, let me mention some of the other diagrams that there are parameters here, and they sometimes matter, they sometimes don't. And of course, we could consider the contributions. We could consider the contributions where it's not just these sources coupled linearly to delta phi, but other higher corrections. And we can assess how much they matter, and they can be small. But it turns out that as we increase the number of points in our endpoint function, they get enhanced by combinatorial factors for any fixed value of the couplings, so that motivates considering them as well. Okay, so in ongoing work, we are looking at the whole distribution. So in general terms, that's a functional integral, the square of the wave function that is calculated in the standard way, just on quantum field theory. Again, including the chi fields, these heavy fields, not prematurely integrating them out. And that generates the appropriate squeeze states and all the diagrams that contribute. So one thing we can do with this that should be, so this business of the overlap of shapes is, it's a blessing and a curse. Means that we don't have a systematic way of constraining non-Gaussianity, period. There are many ways it can be in there, and we can only constrain what we look for. We don't want to look for arbitrary things, because then we'd use up the data to look elsewhere. But one thing that we can do that would be not optimal for any particular model, but could give interesting constraints on anything like this with a growth with n, which means that there's some tail that could compete with the Gaussian, is to look at just kind of a histogram. So add up all the contributions to the CMD map that make a given temperature fluctuation. So, from the field theory we start with, we can calculate what it imprints onto that histogram by just introducing a delta function to enforce that, to count all the contributions that add up to the delta phi hat temperature fluctuation. And again, the nice thing is that these things just add. They don't oscillate away or fail to overlap. So it should give us a way to do some kind of constraining of this quite generally. Of course, we can work it out in detail. It simplifies a lot in special cases, like cases where the shape factorizes, which happened for the first contribution I described. And then you get a nice formula for the non-Gaussian distribution that results. And it will be interesting to see what we can constrain using that. So when it comes to the data, you can do these more crude but basic tests. So this picture is not coming out, maybe, but it's a Gaussian curve. It is a histogram from the data. A little non-Gaussian, there's a gold spot and so on, but it's the thing I described, so you can do this. And that's a very basic thing. It doesn't refer to any particular scenario or any particular dynamics. Of course, once you have such a thing, you want to do the optimal search, which involves the details of those correlators. We expect the sensitivity determined by the level of number of pixels in the data, which is 10 to the 6 or so. So at the level for 3-point functions, it's well known what the optimal estimator is. It's the appropriate dot product of the data with the theory. But even there, it's only tractable if, in fact, there's a good approximation to the shape which has this factorized behavior. Just because of the number of independent sums over L's that we need to do, and certainly for larger n, it just would go out of the realm of possibility entirely to do it the traditional optimal way for all contributions to the shape. The factorized part of it, which is interesting, we can do and we will do at large n, but the other contributions to the shape, which can be enhanced by interesting combinatorial factors, don't fall into this category. So just as a fun question, this is not something this is a question, not an answer, but could it be that these methods, that we could speed up the analysis by using these fancy machine learning techniques that are developing rapidly these days, where neural networks can recognize a cat versus a dog, which is probably not a factorizable shape, could that kind of process be trained to reliably recognize the shape through supervised learning, a shape of non-Gaussianity that we know we don't want to look for, but that can't be done in a reasonable time using the usual methods. So that's a fun question for the future. Here are some pictures of the overlaps, and that shows you a bit of the structure of the shape, and the overlap with equilateral is on this. The overlap with one of these scale invariant shapes that I mentioned is on the bottom here. You see it as the frequency gets appreciable, the overlap is negligible. Okay, so large N theory, the large N being the N of the endpoint function, is interesting. So the signal to noise grows for a large range of N because the noise is given by the variance of the endpoint function itself, and since that's growing, so for sufficiently low N, this is well approximated by the disconnected piece, which is Gaussian, but eventually it catches up and saturates at the square root of N pixels. So the structure of it is basically this. There's some prefactor, which is proportional to our small exponential, times this ratio x, which can be bigger than 1, and that x to the n can just build up. So it's when x is bigger than 1. So even with a small coefficient epsilon, there's this growing x to n, which means we should analyze it better using a suboptimal higher n estimated than that three-point function. So the combinatorics is interesting. These tree diagrams are general, given by partitions of n, because they just correspond to taking the n points and connecting them to the chi fields via vertices with arbitrary numbers of delta phi's. So we just have to add up to the number n of points, and one can easily work out the common fundamental factors that go into that, which turns out to, at large n, enhance certain components of the shape that are not the fully factorized one that I started with. So at the level of the three-point function, you see the structure which generalizes to higher n, where the first line here is a factorized shape. It's a product of three functions, each depending on one of the k's of the triangle. And the last line is basically this resonant shape, where it's just omega log of the total k. But in between, you have things that are factorized products of logs of some sums of some subsets of k's. And those, therefore, are not factorized at large n. The normal methods are prohibitively time-consuming, so this is where we want to see about that, see if there are other ways to do it. There is at least still this factorized component of the shape, whether it dominates or not, and even with a slightly suboptimal estimator, we can do better with that at large n than at the three-point function level. And as long as, for these individual factors, we have a good approximation to the shape, then we can constrain the parameter in a way that's very insensitive to the overall size epsilon, so you're dependent on the small density, which comes in to the 1/nth power. So that's the plan to start with. Since I've emphasized how, to me, it's quite interesting how, again, this data that's telling us about things that was going on 14 million years ago is so sensitive to details, right? You can, again, easily have these non-overlapping shapes generated by different kinds of dynamics, and that's really a big opportunity. Even if things are null results, you learn, if there's a well-defined thing that's being tested, you learn a lot from that. And so anyway, it raises many questions, such as what about the Kinsey string production? So here we did a very detailed quantum field theory analysis because we wanted to have a reliable shape to test, and particles are interesting. Now some particles appear in string theory and field theory space. But by the same token, you can have time-dependent tensions in the same way. So you can have some wrapped grain fields in the quant whose tension changes with time in a similar way. And this is a really interesting and subtle theoretical problem to calculate that. We have a WKB estimate for, say, a circular string developed in some of these collaborators listed up there, which has an interesting feature that it favors, there's a part of it that favors larger strings if the minimal tension isn't too small. And in any case, the point is it behaves rather differently from the particle production process. So the result, if one wanted to constrain or test for this going on in the inflationary period, it would be another calculation, which would need to be precise enough in detail to give a shape that can be tested in a meaningful way, or maybe this can fall under the more general but less the more general model independent but suboptimal constraints I mentioned earlier. But anyway, for strings meeting, I definitely wanted to mention this. We're also looking at whether the statistics of these produced particles could imprint in a measurable way on the observables. Okay, so here's a summary. I think I've said all this. This non-adiabatic dynamics. Again, just reasonable order one coupling scales that are expected can lead to a new form of non-Gaussianity, both in the shape and the growth of the n of the endpoint function. It's sensitive to details, sensitive to its high mass scale, but also the details of the mass function. There's more one could play with in that vein. This is partly motivated, since it's part of a complete treatment of the phenomenology of active monogamy, which is going to be tested also by R in the next round. And we'll see what happens when the data is under analysis still, with some of the possibilities needing more work to understand how to do the as close to an optimal analysis as we can. And again, this bottom-up effective field theory really has to be supplemented by these fields, even though they're extraordinarily heavy. So there's a question of whether we could. You should get the impression that this study of non-Gaussianity is a neat package that's been constrained and then we're doing large-scale structure. It's not that easy. Even at the truly single-field level, we're not done. And as we've seen here, this truly single-field level is not reliable if there are particles or strings that are even up at this phi dot scale. So let me stop there.
Okay, thank you very much.
I just had a question about the data analysis part.
Yeah.
So it seems to me that the large-scale structure community has similar challenges of constraining PDFs of the galaxy distribution function, and they use some techniques of or measuring the skewness and composits of the PDF directly. Is there anything useful to be extracted from?
Yeah, except when I mentioned Poisson statistics, it's in time. These different events are uncorrelated in time, but in space they're not. So it's not exactly the same problem, but yeah, the point source estimators are kind of an analog.
I just mean quite generally also for them it's less useful to express things in terms of just the pi spectrum, but they have to look at the full PDF.
Yeah, right.
So I'm just wondering if there is.
Oh, if that's already. Yeah, that's a nice question. I'm not sure. Yeah, I'm not sure there if they have this issue with the separableness of the shape or not, for example, as well. But yeah, that's a good question.